Welcome back, everybody, for this week's IPAC. So there will be a talk on Thursday by Sean as well. So we'll have two talks, and then next week we'll start a new series. And here's Sean with lecture three.
Thanks for having me again. Um, Let me just remind everyone about the goal. The goal for today is um, to prove the skewing formula. Um, so k minus 1 to the n minus k, um, and e. I forgot to write this down ahead of time, which is why I'm writing it now. Um, so perfect. Um, so the ultimate goal of these talks is to understand this identity geometrically. Maria already talked about proving this identity combinatorially and algebraically. Um, and today I will hopefully finally prove this at t equals 0 geometrically. Um, this is something that Maria and I proved previously before we started collaborating with Eugene. And then on Thursday, um, seeing proving the whole thing, or yeah, or let me just say, explain the identity uh, not setting t equals to 0 using affine Springer fibers. And kind of the upshot, t equals 0 is so sort of my starting point is so at t equals 0, this side is going to be up to reversing and applying omega, the Frobenius characteristic of the cohomology of this particular variety I talked about earlier. Um, and then at t equals 0, this side is really just a Hall-Littlewood polynomial. Um, whose cohomology is a Springer fiber. Um,
So,
yeah, so the
Sean.
point of this talk is understanding why those two cohomology rings are related. Um,
Oh, sorry, Sean.
yeah.
Jake has a question on the chat asking you if you can say briefly what the Q parameter ends up meaning geometrically.
Q just means cohomological degree.
Oh, then I should have
But
asked, what does T, sorry, yeah, I meant to ask, of the two parameters, what does the other one end up meaning geometrically?
okay.
Sorry.
So yeah, so Q is what we did, right? What Jake, Alex, and I did on the left-hand side, Q being cohomological degree. The other parameter T will come from the affine Grassmannian. So it will be coming from this extra T parameter. We'll be working over we'll be working over Laurent series instead of just like vector spaces over Laurent series rather than just vector spaces. And the T will be in the parameter in that
Okay,
field.
thanks.
Yeah. Okay, so last time I set up this like basic diagram of, or I shouldn't call it basic, but fundamental diagram of commuting diagram of Springer theory, where on the right-hand side we have the what's called the Springer resolution of the nilpotent cone. So n here is the nilpotent n by n matrices, And tilde is, I guess I wrote it above somewhere. Um, so um, pairs of complete flags together with nilpotent matrices such that the nilpotent sends the ith part of the flag into the ith part of the flag. Um, and there are a couple of ways of modifying that. One is just to allow any matrices instead of just nilpotent ones. And then above here, the tilde means pairs of flags and matrices with the same condition. But then you can restrict to the regular semi-simple part, meaning regular semi-simple, meaning diagonalizable with distinct eigenvalues. And again, define pairs of flags and regular semi-simple matrices with the same condition. And the important part of this diagram is essentially what we're trying to do is construct some kind of symmetric group action on the fibers here. And there really isn't a space level action, but there is a space level action on this left-hand vertical arrow, because if you restrict to semi-simple matrices, then and you have this condition, then each piece of your flag breaks up into eigenlines for that matrix. And then the SN action is really just permuting the eigenlines. And then so essentially you get this SN action on the fibers over regular semi-simple matrices permuting these lines. And I kind of black boxed this, that you can apply the theory of perverse sheaves to transfer that action to fibers of this map, but with the exception that it's not on the actual fibers, it's really on the cohomology of the fibers when you transfer it. And then you can restrict to fibers only over nilpotent matrices.
Pardon me, Sean. So if you look at the fibers of rho, you're getting essentially Hall-Littlewood polynomials. But
Mhm.
if you look at this larger map, rho prime, I mean, if I take an arbitrary n by n matrix, and put it in Jordan form, from that data, can you tell me the Frobenius image of the action on the fiber, or the graded Frobenius image? Is it like some kind of product of Hall-Littlewoods, or
Yes, it should be some kind of product of Hall-Littlewoods where you break it up by
the
whichever
eigenvalues,
is,
or
yeah, the distinct eigenvalues. I've never actually checked that it's literally the product, or yeah, I've never checked if it's literally the product or something else. I mean,
well, regular semi-simple, it's like discrete points. So you have something in cohomological degree 0, but the regular representation, right? So
sorry, can you say it again?
so if you look at the regular semi-simple locus, any
Mhm.
fiber looks like in factorial distinct points that carry the
Yeah,
regular representation. So that's going to be something concentrated in degree 0, but like, P1 to the n in degree 0. So
right.
somehow, um, yeah, I mean, it feels like it should be something like a product, but
Yeah, yeah. Um,
uh, yeah, Jake, I think the n
uh,
factorial points is an induced
yeah.
representation. Yeah, I mean, induced trivial from the trivial subgroup all the way up to Sn. That's right.
Mhm.
Which in Frobenius
Um,
characteristic is multiplying, but
I I tried to think about this at one point, and I think if you have multiple eigenvalues of multiple different eigenvalues, it's not quite a product of Springer fibers, but it is sort of similar to that. And there's some kind of extra counting you have to do. Maybe
hmm.
it's
mhm.
like finitely many, some kind of finitely many union of finitely many products of
Right.
Springer fibers or something like that.
Hmm.
Right. But at least, yeah, it's at least believable that maybe you can write it in terms of Hollywood somehow.
I think I think like you probably can figure out exactly what it is. But because it has something to do with describing what do you call it? The commuta or the centralized, whatever it is, the matrices that commute with the given matrix. And the condition to commute with the given matrix like splits across distinct eigenvalues, but is more complicated to describe for like say a nilpotent matrix or a matrix with one eigenvalue and some Jordan type. Um,
Right. So I mean, at a space level, you're getting a disjoint union of things that look like smaller copies of.
yeah, that's sort of what
Yeah,
I
yeah, but then of course the perverse sheaf machinery is required for an action, and that's on the cohomology. So I don't know.
right.
Yeah.
Hmm. I mean, Martha is saying she doesn't think it's a product, but someone should write it down.
Yeah, yeah.
Because yeah, I feel like this question has come up a lot. Um, or maybe someone has written it down, but I don't know where to find it. Okay, so the significance of the symmetric group here is that it's the Weil group for GLN. Um, and so when Springer defined these varieties, he proved several things about them. So first of all, you can calculate the dimension. Uh, or let me say, um, so I'll use this notation mu to mean the sum, or sorry, n of mu to mean the sum of the conjugate parts, the binomial coefficients, um, where you take the conjugate partition and sum up these binomial coefficients. And it turns out that this is the dimension of the Springer fiber corresponding to mu. Actually, if I don't remember if it was Springer or Spaltenstein that proved this, but um, this actual formula. But he did prove that if you take the top cohomology group of the Springer fiber, there is an SN action on that group, and it's isomorphic to an irreducible. Um, yeah, as SN representation. You can generalize this to other Lie types. The statement is a little bit more technical, so you have to also consider the action of the component, what's called the component group of the nilpotent matrix, in order to actually zoom into a particular irreducible. Or yeah, sheaf theoretically, you have to run over irreducible local systems on the nilpotent cone. Um, and Lustig and Procesi, not in these words, but they in some form proved that if you take the Frobenius character of this SN action, um, so if you turn it into a symmetric function via the Frobenius character, and keep track of the cohomological grading, you get exactly a modified Hall-Littlewood polynomial. Um, and since we will need it, I also wrote down the definition of this delta Springer fiber that Jake, Alex, and I defined. They're partial flags in this large dimensional vector space with the Springer condition, but then this extra kernel condition, and for a particular Jordan type. Okay, Alex, Jake, and I have a slight generalization of this, but we only need this version for now. And what I'd like to do is explain how this one also fits into the story. But we need some constructions of Borjo and McPherson to say what the connections are. So for each composition, there's something that sits in between the Springer resolution and the nilpotent cone. So originally I had this map where you're keeping track of complete flags and nilpotent matrices, and then the map down to the nilpotent cone is just remembering the nilpotent matrix. But you can do this for any partial flags. And in between these things is partial flags for some fixed alpha with nilpotent matrices such that the nilpotent sends the ith piece into the ith piece. So in some sense, this is, well, yeah, maybe I'll not go there yet. And a couple of things that makes the theory work, like why you can analyze these maps so nicely in terms of cohomology of fibers and perverse sheaves. So the following two properties are important, that all maps in the picture are what are called semi-small. And I'm happy to write down the definition if anyone wants, but as roughly what this property is saying is that the fibers, the dimensions of the fibers are not too big. But usually you phrase this in terms of some stratification of the target of the map. And the larger the stratum, the smaller the fibers need to be. So it's really a condition on like which fiber in which stratum are you taking. But in some sense, it controls very well what the geometry of the fibers. And the second condition is that each of these things sitting in between is, I mean, it's not smooth, but it is rationally smooth. So this one is smooth. And this map is a resolution of singularities. But in between, as you vary alpha, these are rationally smooth. And essentially what this means is that the local cohomologies are are the same as the local cohomology of a smooth variety. So at least for many calculations involving local cohomology or cohomology, you can kind of imagine that it's smooth, even if it's not. And essentially, so you can try to, put these things through the machinery of Springer theory and try to construct an SN action. There's not quite an SN action, but there is an action of some symmetric group, not the full symmetric group. So you can do the same setup where you have alphas and then partial flags here allowing any matrix, and then partial flags allowing only regular semi-simple matrices. So this one is so pairs of flags and matrices, or partial flags and matrices, or regular semi-simple matrices, such that XVI is in VI. And then, so how do you see which symmetric group acts on this? Well, basically, so each quotient, so this is dimension alpha I. So it's a direct sum of alpha I eigenlines. And basically this gives you an action of what's called the relative or partial Weyl group. So I'll call this W alpha. And essentially, to describe it in words first, it's the permutations of the parts of alpha that are equal. So if you imagine like swapping the different parts of alpha, you're only allowed to swap parts that have the same size. And then just take all of the permutations you get that way.
Sean, is this then basically a Young subgroup? Maybe conjugate to a Young
Yes.
subgroup? Okay.
Yes. So that, yeah. So let me write that down next. So it's a product of symmetric groups, a Young subgroup, where alpha I prime here is the number of parts of size I. Or for the Lie theorists in the audience, this is the normalizer of the levy, modulo the levy. And so if alpha is parts of size all one, then the levy is a torus, and then you're doing n of t mod t, which is the usual Weyl group.
So somehow, should I think about this as taking the previous picture and taking parabolic invariance, like S alpha invariance, and then that's going to carry an action of your W alpha group?
Um,
So like if I have any SN module, I can take the S alpha invariant submodule, and that submodule will carry an action of W alpha.
I think that's right.
I think the
Um,
answer is yes. I'll avoid it.
Yes.
Okay.
So, the thing to not confuse this with is it's not SN mod Young subgroup,
Oh no. That's
which
right.
is, yeah, which is not what you're saying. I'm
No,
just
no,
pointing
no, no, because
out.
it's a group action, and like usually that quotient, like that's not a normal subgroup, but it's like if you take the S alpha invariance, you get something strictly smaller. But then
Mhm.
that smaller thing is going to carry an action of anything in the normalizer of S alpha, but S alpha will fix everything. And that's that quotient normalizer of a levy mod a levy that you wrote down.
Yes. Yeah.
And
Okay.
I can
And
also
this,
just say, can I, oh, okay, because I just looked this up this week. In Borho and McPherson's paper, where they do these like partial resolutions, they prove that the S like the invariance of the Springer fiber representation under a Young subgroup is isomorphic to homology of a Steinberg variety, and then the
Yeah.
twist invariance is a Spalmstein variety. So I think that's
Mhm.
lining up with Brendan's question.
Thank
Yes,
you.
and this will this will come up. I mean, this is also an important part of what I'm trying to say in terms of skewing. It took me a little while to process how Brendan said it, but he said it well, just not in different words. Okay, and then the upshot is that you get an action of this W alpha on the yeah, the cohomology of the fibers, which is what Martha is saying. But there's also a more refined statement of this, which I will also need. And essentially, yeah, so essentially what happens is we have this, right now I'm only saying something about actions on cohomologies of fibers of this map, but basically what I need and what Borjo and McPherson considered is this thing breaks up into strata, and you can restrict the map to those strata and look at the cohomology of those fibers. So yeah, n tilde alpha has a stratification by these O. I like to call them or write them as in terms of tuples of partitions because we're in type A. So we have a tuple of partitions where each partition is a partition of alpha I. And then O lambda is the space of partial flags and nilpotents. Such that we still have this Springer condition. And so that's just coming from the N alpha tilde construction. But the stratum is given by basically specifying the Jordan type of the action of the nilpotent on the quotient spaces. And essentially what happens when you take the closure is that you have the same definition, but now the equality turns into an inequality on Jordan type with respect to the dominance order. So this is dominance order on partitions that the sum of the first j parts of the first partition has to be less than or equal to the sum of the first j parts of the second partition for all j. And Borjo and McPherson were studying the fibers of this over these strata. So take your stratum closure, include it into this partial resolution, and then this is just the restriction map down to the nilpotent cone. And the Borjo-McPherson variety is the fiber over a nilpotent but restricted to this fiber. So this is partial flags. And then the same Jordan type condition. So n acting on this quotient space is dominated by lambda I for each I. And so we've already talked about fibers of this map, and I just defined fibers of this map, or like fibers of this map over strata. But the third part of the picture is fibers over this map, so going from full flags to partial flags. And we also need that data in order to relate all three maps. So what does the fiber over a pair, flag and nilpotent matrix? Essentially, this is a partial flag, and you're extending it up to a complete flag. So it's all complete flags, such that this complete flag extends the partial flag, meaning like the the alpha ith piece, that the dimension alpha 1 piece of W is equal to the first piece of V, and so on. And together with this nilpotent, or the Springer condition. But then what does this look like? So you have your partial flag. So on. This quotient is dimension, sorry. This jump is in dimension alpha 1. This jump is in dimension alpha 2, alpha 3, and so on. And then to build W, you're filling in a complete flag from 0 to V1. And so on. And then you're filling in a complete flag from V1 to V2 and so on. And so this just breaks up as a product space, a product of usual Springer fibers. So it's the product of Springer fibers where the operator in the ith piece is what you get by n acting on the ith quotient space. And Born-Macpherson's theorem, or one of their several theorems in this paper from 1983, is that the cohomology of each of these fibers is related in the following isomorphism under some rational smoothness condition. So if your stratum is rationally smooth, at every point of the fiber over the stratum, every point of this Born-Macpherson variety, then you get the following isomorphism of between cohomology groups. So on the one hand, we have the Born-Macpherson coming from those fibers. On the other hand, we have like a generic fiber here over or a fiber here over a generic point in the stratum. So this is for a fixed pair. In the orbit, not the orbit closure. And that tensor product of cohomology groups is isomorphic to cohomology, but shifted in degree of the fiber of the full map. Except with one caveat. It's not the full cohomology. It's a particular isotypic component. So I will explain what this notation means in a second. And it connects with what Brendan and Martha were talking about, and Jake. So let's say given Sn acting on some representation W, and some young subgroup in Sn, we can take the restriction of this representation down to the Young subgroup. And that'll break up into finer representations. And then we can take the isotypic component of a tensor product of irreducibles. So I'll define W upper this tensor product of irreducibles to be the isotypic component of this particular irreducible.
So Sean, just
Um,
the notation about the V's being parts of flags versus V's being representations, or is it like it's the same thing, but you're just saying, okay,
Yeah,
it's part of the
sorry.
flag and it's carrying this SN action.
Yeah, sorry. These V's are representations. I was, and this is this one is flag.
Okay.
And just another notational thing. Okay, so you have a parabolic subgroup of Sn, like S lambda upper 1 up through S lambda upper L. So the lambda upper i's, are those partitions?
Oh, sorry. Sorry. I meant the size. The size. Yeah. Sorry. Lambda upper I
That's
is a
just your alpha
partition.
then, right? To use the
Yes. Yeah. Okay. Yes. Yeah, exactly. Let me put alphas there. Thank you.
Okay.
Yeah, exactly. Um, yes. Oh. So one particular one of these statements is if you take the full fiber, if you take the entire stratum, when the stratum closure is everything, then this is saying take invariance. And there's another stratum that corresponds to taking anti-invariance. And so taking invariance, when you take invariance, you get what some people call the Steinberg variety. And when you take anti-invariance, you get what people call the Spaltenstein variety. By anti-invariance, I mean the isotypic component of the sign representation. Right, so essentially, and also related to what we were saying before, is that each of these sides, so Borjo and McPherson didn't say this exactly in their paper, but you still have you still have this W alpha action floating around. You can, you can figure it out from what they wrote from their calculations that this W alpha still acts on both sides of this isomorphism. Um, it acts basically it acts here, trivially here, and just like we can just think of this as a vector space, and it's even just sitting in a single degree, so it's not even a graded vector space. And then it's also acting here because when you take this isotypic component, you still have this relative Weil group action sitting around. So really, this is an isomorphism of W alpha modules graded. Well, yeah. As you sum over I, you get an isomorphism of graded W alpha modules.
So is this somehow where the perps are coming in? If the vector lambda is
Yes.
like 1, 1, 1, 1, 1, and then
Yes.
lambda, this is going to basically
Yes.
be an S lambda perp with the degree shift.
Yes, exactly.
Okay.
So right. So in the last 18 minutes, first of all, I want to connect these constructions to the delta Springer fiber. I mean, the statement is here, and I'll prove it for you. Second, I'm not sure if there's enough time to go through this rational smoothness check in full. So there's this annoyance of like, okay, this only works for rationally smooth. And somehow, a miracle happens that because of the combinatorics we're doing, rational smoothness checks out. But the rational smoothness isn't always, I mean, it's not given. You have to, there's some combinatorics that goes into checking why the rational smoothness condition is true. And then third, basically, maybe what Brendan already did in his head, translating this isomorphism into a statement about skewing symmetric functions. And yeah, the spoiler is that taking isotypic component is related to skewing out.
Sorry,
Skewing
I have a
by
question about what if you could scroll up a bit where you put isomorphic as W alpha, but like just because like alpha I equals alpha J doesn't mean that lambda super I equals lambda super J, right?
right. Yes.
So, okay, okay, I'll think about it. I might have to ask you afterwards about given, let's say lambda I is not equal to lambda super J and alpha, just have
Yeah,
that.
okay. You might be right. I might need to be more careful here. Because Maria and I only yeah, you might be right. Maria and I only checked this. I mean, we only wrote down why this is true when the lambdas are equal for parts of equal size.
Or
So
or kind of for skewing purposes, you only ever have to consider like 1, 1, 1, 1, 1, 1, 1 lambda
yeah,
and
true.
get away from this issue Monica's pointing out. But yeah, it would seem like you would need
Yeah,
a stabilizer of the tuple.
okay.
Like
Yeah, okay, let me put a caveat here. Um, in the following case that we care about.
Okay, great.
Okay. Yes. Okay. So why does the delta Springer variety fit into this picture? So I'll remind you of the definition. We have partial flags of this particular type. Alpha, or I already wrote down alpha down here. Alpha has n parts of size 1, and then a large dimensional piece. Um, and then we impose these two extra conditions. This one is obviously coming from the constructions above because I always had that condition. But then where's this condition, or how does this condition fit into the above constructions? So this is, or what I'm going to write down is particular to rectangular Jordan type. So since the Jordan type of n is rectangular, then the kernel, which I've written here, is equal to the image of n after applying it n minus k times. If you want to think of this visually in terms of vectors, previously I defined this nilpotent by putting basis vectors in and then saying, okay, n moves everything to the right. And then when you get to the right side of the rectangle, it just goes to 0. And so the kernel is the vectors in the right-hand side in that rightmost column. But it's also equal to the image of applying this n minus k times because like as you move over n minus k times, you only see those k vectors in the image. So I wrote kernel of n previously because it's an easier condition to write down. But really, I'm thinking of it as this image. And so if you have one of these partial flags in the delta Springer, oh, sorry, so let me first take a flag that satisfies this condition. Then the flag satisfies the delta Springer condition if and only if V contains the kernel. But we just saw that this is the same as the image of the n minus k power. But then what's the image of the n minus k power? It's n minus k applied to the full vector space. Or another way to put this is that n minus k sends, so since n to the n minus k sends the full vector space into Vn, then it's acting by 0 on the quotient. But then you can translate that in terms of Jordan types. So it's the same as saying that the Jordan type of n minus k. Sorry, it's the same as saying the Jordan type of n acting on this vector space, or this quotient is sorry, let me say it this way first. It's saying that basically all parts of the Jordan type are less than or equal to n minus k, which is the same thing as saying that the Jordan type of n acting on this quotient, this one is Vn plus 1, is dominated by the partition with parts all size n minus k. And that's exactly the condition on the Bohrhoff-McPherson variety. So it's the one where the partitions are all trivial of of size 1, but then in the final one you have this rectangular partition. So it kind of sits inside of the big rectangle like this. So this is k minus 1 and this is n minus k. Any questions on that? So yeah, so that's how it connects to Bohrhoff-McPherson. Just translating it into a Jordan type condition, which was not obvious to Alex and Jake and I at first. It took a couple of readings of Bohrhoff-McPherson to parse this or to figure that out. And then second, I wanted to quickly explain why is this thing rationally smooth on this other thing, on the Bohrhoff-McPherson variety. Essentially, what this comes down to is, I mean, it's also combinatorics. So checking rational smoothness of some variety at some point. Um, uh, Actually, let me state this as in a neighborhood of some point is equivalent to checking particular intersection cohomology groups are trivial in a neighborhood. Or like as x varies in a neighborhood. Let me say x prime. So checking rational smoothness is at some point is not equivalent to checking a one intersection, local intersection cohomology group is trivial. You really have to do this in neighborhoods. But there's this theorem of Lustig, that says that computing intersection cohomology groups of nilpotent orbit closures is the same as, I mean, you get these modified Q-Kostka polynomials. So here, O lambda bar is the set of nilpotent matrices with Jordan type dominated by a single partition lambda. And n here And here is some nilpotent matrix with Jordan type mu dominated by lambda.
Sean, is it a
Yeah.
coincidence that that's essentially the graded isotypic component or its Hilbert series for the lambda component of the Hall-Littlewood?
It's not a coincidence, and it comes from an application of the decomposition theorem for the Springer resolution.
Okay,
I just didn't want to
it's okay.
explain. I just didn't
No,
want to go
no,
into
no,
the
no. I
composition
couldn't help but
theorem.
notice that it's yeah.
Yes. Um, uh, yeah, essentially what happens is you take the constant sheaf on the Springer resolution, and push it down and apply the decomposition theorem to that. You'll get a direct sum of intersection cohomology complexes tensored with some coefficient groups. And the coefficient groups carry the SN actions. They turn out to be the irreducible SN representations. And the intersection cohomology groups, well, their stocks are these local intersection cohomology groups.
So
So
these
that's the
multiplicity spaces, basically.
yeah, exactly. The multiplicity spaces of these SN representations.
Cool. Thank you.
So this is shape lambda and content mu tableau, keeping track of the co-charge statistic. And I'm not going to exactly explain like how these two things are connected, but like essentially computing these intersection cohomology, local intersection cohomology groups comes down to computing the ones for a single partition of that shape. And you can control like which points do you actually have to check on that orbit closure. And the combinatorial tool that we needed, the combinatorial fact that we needed is that if you have any partition of n minus k times k minus 1, basically the size of that partition, such that mu is contained as a Young diagram in this rectangle. So n minus k by k. Then the intersection cohomology groups are trivial. So these k tildes for rectangle are just it's just a single power of q given by the n statistic of that rectangular shape. And the significance is here mu runs over all mu. I mean, the significance of the mu is that mu is the possible Jordan types you could get. Of the action of n on this quotient space. For partial flags in the delta Springer. And maybe I will leave it as an exercise, or you can ask me to do it in a second during questions. An exercise is to check it, prove it. The proof is quite cute, and you can see it kind of easily if you do it enough examples.
So just proof aside, in terms of the statement, you're saying, it's contained in the rectangle, but isn't that just the same thing as saying it's dominated by the n minus k to the k minus 1? You're saying all the parts have to be less than n minus k, even though it can be a little tall. Oh, I see. The point is it can be so tall. You're also saying it has less than K parts.
Yeah, exactly. Less than or equal
Okay,
to parts and dominated by this.
okay,
By
got it. I was missing. I was like, that's why doesn't it? Yeah, thanks.
Yeah,
You
it
just
should.
had one semi-standard tableau that's contributing that code. Okay.
Great.
And the length of mu is at most K. Yeah. And yeah, and then the final piece is how do you translate this to the skewing formula? Maybe I should do that next time quickly, since we're already at the end of time.
All right. Thank you so much. That's
And then maybe I
fun.
should just say next time the affine Springer fiber case. Yeah.
Okay, great. It's fascinating. Any questions for Sean before we adjourn and hear about the full QT thing next time?
So I do want to say, like, yeah, this talk was also a little bit technical if you've never seen Springer theory, but at the beginning of Thursday, I will draw lots of pictures of lattices and match up. Like I want to explain well the connection between lattices and like terms in the shuffle theorem. So if you're like more of a combinatorialist, stay tuned for like some more bijections.
Okay, let's thank Sean again, and we'll see you all on Thursday, hopefully. I know I'll be here. Survive the heat, those of us on the East Coast.
Right. See everyone.
Thanks, everyone.
Hey.